Hello dear students, continuing the lecture series for mechanics. Today we will study about Rutherford scattering. So it is a scattering of a charged particle from the nucleus, and in this we will study the interaction cross section for the scattering of a charged particle from the nucleus. So here we consider a coordinate system. So this is the x-axis, let this is positive x-axis, negative x-axis, and say this is the origin, and on the origin there lying a nuclei of charge plus Ze, and we have a scattering particle that is incident and that is having a charge of Z dash E. Z dash is the atomic number of the incident particle and capital Z is the atomic number of the heavy nucleus, and let this is having the coordinates r and theta at any time t. So as it is having coordinates r and theta at any time t, so if we try to draw the this is the direction of the incident particle, and as it will be moving towards the nucleus, so it will cover a path like this. So this will be a hyperbolic path, and soon we will derive the fact that why this will be a hyperbola and what will be the interaction cross section for this scattering. So we draw the asymptote. These are the two asymptotes drawn on the trajectory of the scattering particle. So as coordinates are r and theta from the nucleus, then this separation this will be r, let this point be p, then OP will be equal to r, and let this angle is equal to theta. This angle is theta, then this angle is also theta. Let this is the incident direction, let this is equal to phi, then this angle and this angle are also phi, and this is the scattering direction. So this is the problem that we are to deal with today. So this is the Rutherford scattering of a charged particle from a heavy nucleus. So consider a positively charged particle of charge Z dash E moving towards a heavy nucleus, moving towards a heavy nucleus Ze, having charge Ze. The Coulomb force is given by, they will exert Coulomb force on each other. So the Coulomb force between them is given by it is having a standard formula. What is the formula for Coulomb force? 1 by 4 pi epsilon naught Q1 Q2 upon R square, and here first charge is ZE, second charge is Z dash E divided by R square. So it will be written like F is equal to 1 by 4 pi epsilon naught Z dash E square upon R square, and it can be written as equivalent to a central force problem we have dealt with one of our previous lectures, where we write the force equivalent to minus K by R square. So comparing the two, we will get the value of small k equal to minus 1 by 4 pi epsilon naught Z dash E square. So we mark this as equation number 1, because we will solve the Rutherford scattering problem on the basis of our previous knowledge of central force problem that we have studied in previous lectures in detail. The total energy of the particle is given by total energy of the incident particle. So we say of the system is given by E, it is equal to half mu V square. Here mu is the reduced mass of the system. So take into consideration the concept of reduced mass, we are not having now two particles, nucleus and incident particle separately, rather we have a single mass moving with velocity v. So mu is the reduced mass of the system. So mu is the reduced mass of the system. So from here the value for velocity it will be like this. So we mark this as equation number 2. And equation of trajectory of the particle is given by general equation of trajectory in general of the incident particle, or we can say scattered particle, is given by 1 by R, it is equal to 1 by L 1 plus E cos theta. So this is equation number 3, where small l, what is small l? Yes, semi-latus recta. And what is small e? Eccentricity. So dear students, we have studied in detail regarding the trajectory of the particle in the articles of central force problem, and there we have derived this equation number 3 in detail and derived the expression for semi-latus recta and eccentricity. And those expressions we will be using here. Small l, it is capital L square upon mu k. Mu is the reduced mass, capital L is the angular momentum of the system, and for the eccentricity we have derived the general formula 2E L square upon mu k square. So these formulas we have derived in our previous lectures of central force problem chapter. So now we draw a perpendicular on the asymptote here, and we mark this as n, and that this ON is equal to B. So this is the perpendicular distance, or we can say impact parameter. So ON, we assume it equal to B, and it is the impact parameter of scattering. And capital L, angular momentum of the moving particle. Angular momentum of the system, and it is equal to linear momentum into perpendicular distance. Angular momentum is equal to linear momentum of the system into perpendicular distance. So value of V from equation number 2, yes, from equation number 2, it is 2E upon mu into On. On is our B, so it is 2 mu E into B, or 2 mu E into B square if we take it inside the square root sign. So from 5 and 6, centricity will come out to be 1 plus 2E into L square. L square is 2 mu E B square upon mu K square. So when we solve this, what we will be getting? 1 plus 2E, 2 mu E B square divided by mu, and value of K square. Value of K is equation number 1. So it is 1 by 4 pi epsilon naught negative sign z dash E square whole square. So if we solve this, we will be getting 1 plus 8 pi epsilon naught EB upon z dash E square whole square. So we mark this as equation number 7, and as from this you can get E is greater than 1, so path of the particle will be hyperbolic. So path of particle will be hyperbolic in nature. So if a centricity is greater than 1, then the path will be hyperbolic in nature. So now from the diagram, if you will see this, these three angles are linear angles. They make a linear triplet. So phi plus theta. So from diagram we can get phi plus theta plus phi, it is equal to 180 degree. So 2 phi, it is equal to 180 degree minus theta. So phi is equal to 90 minus theta by 2. We mark this as equation number 8. So for asymptotic solution, when the particle is at infinity, angle is equal to phi. Scattering angle is equal to phi. So from equation number 3, 1 by infinity is equal to 1 by L 1 plus E cos theta, and instead of theta we can write now phi. So 1 by infinity is 0, 1 by L 1 plus E cos phi. So 1 plus E cos phi, it is equal to 0. E cos phi, it is equal to minus 1. Cos phi, it is equal to minus 1 by E. So cos phi, value of phi from equation number 8, it is cos of 90 minus theta by 2. It is minus 1 by E. Cos of 90 minus theta is sin theta by 2. It is minus 1 by E. So cosecant theta is by 2 is, if we take the reciprocal, minus E. Cosecant square theta by 2, it is E square. So adding 1 on both sides, cosecant square can be written as 1 plus cot square theta by 2. Yes. So cot square theta by 2, it is equal to e square minus 1. So cot of theta by 2, it will be square root of e square minus 1. So we mark this as equation number 9. So now we have centricity equation 9 number, and this is 7. So from 7 and 9. So from 7 and 9, cot of theta by 2, it is equal to e square minus 1. So it is 1 plus 8 pi epsilon naught e b upon z dash e square whole square minus 1. So this cancels out, square root and square, they again cancel out. So we will get 8 pi epsilon naught e b z dash e square. And from this we can get the value of small b as z dash e square divided by 8 pi epsilon naught e cot of theta by 2. So we mark this as equation number 10. So if we differentiate this, then it will be z dash e square 8 pi epsilon naught e, these are constants. Derivative of cot theta is minus cosecant square theta by 2 and 1 by 2 for derivative of the angle. So dB by d theta, it will be equal to minus z dash e square divided by 16 pi epsilon naught e cosecant square theta by 2. So we mark this as equation number 11. So as we know that the differential scattering cross section is given by scattering cross section is represented with the sigma symbol minus b upon sine theta dB upon d theta. So if we substitute the various values, so here we will be getting this value of small b is z dash e square upon 8 pi epsilon naught e with negative sign is already there, cot of theta by 2, and in the denominator we have sine theta, so we can write it 2 sine theta by 2 cos theta by 2 into minus z dash e square 16 pi epsilon naught e cosecant square theta by 2. So if we solve all these things, what we will be getting, our scattering cross section, it will be, so you can also write here SC for scattering, or rest is on your wish, z dash e square whole square upon 16 pi epsilon naught e whole square. Because this cot theta, it can be written as cos theta by sine theta. Cos theta will cancel out, sine theta will remain 1 over sine theta. So it will be 1 over sine raised to power 4 theta by 2. So this is the very important Rutherford scattering cross section. And what you get here, scattering cross section, it is inversely proportional to sine of power 4 theta by 2. So this is very important result. Now we do a special case, because Rutherford scattering was mostly studied for alpha particle. So for alpha particle, we simplify this relation. Z dash is equal to 2 for alpha particle. So sigma theta comes out to be, it will be 2ze square upon 16 pi epsilon naught e 1 by sine raised to power 4 theta by 2. So after a little more simplification, because 2 square and it will cancel out here, so it will be ze square whole square divided by 4 into 4 pi epsilon naught capital E square 1 divided by sine raised to power 4 theta by 2. So this is the scattering cross section for alpha particle, because Rutherford scattering was mainly introduced for scattering of a alpha particle from a gold nucleus. So dear students, you might have studied Rutherford scattering in lower classes, but today we have dealt with the mathematics behind the scattering, and what we have studied that the path of the particle be hyperbolic in nature and cross section is inversely proportional to sine power 4 theta by 2. So this is all for today. Keep in touch for next lectures. Thanks a lot.